X-rays were discovered accidentally on November 8, 1895, by German physicist Wilhelm Rontgen when he was investigating cathode rays. He noticed a glow on his fluorescent screen even though there was a piece of black cardboard between his very high-voltage cathode ray tube and the screen. The glow was evidently caused by some mysterious invisible radiation that could pass through cardboard. Because of the mysterious nature, Rontgen called this radiation X-rays. He discovered that these radiation rays could render many objects transparent, and he soon realized that a photographic plate can capture the image. So he took the world's very first human body X-ray image of his wife's left hand on December 22, 1895. When Mrs. Rontgen saw the picture, she said, "I have seen my death." And here is that picture. Within months, hospitals everywhere were using X-rays to see broken bones. Rontgen won the first Nobel Prize in physics in 1901. A basic X-ray tube is like this. This voltage is used to heat up the filament, and that voltage, usually a few kilovolts to about 100 kilovolts high, is used to accelerate electrons from the hot filament cathode. When the electrons strike this metal target anode, they lose at least some of their kinetic energy. Because of the deceleration, they give off EM radiation, X-ray photons. Here is what a typical X-ray spectrum looks like for the X-rays produced by an X-ray tube like this one. The continuous spectrum part is called Bremsstrahlung X-ray. Bremsstrahlung in German means braking radiation, because these X-rays are produced by decelerating electrons. These sharp peaks, the discrete part of the spectrum, is called characteristic X-rays. Those electrons accelerated by high voltage can knock out one of the inner shell electrons in the metal target, and when an electron in an upper state transitions down to fill the vacated lower state, a photon is emitted. The K lines are transitions into the K shell. The innermost n equals to 1 shell is called the K shell. A K alpha X-ray photon is emitted when an electron falls from the L n equals to 2 shell to the K n equals to 1 shell. A K beta X-ray photon is emitted when an electron transitions from M n equals to 3 to K n equals to 1. So the wavelengths of these characteristic X-rays depend on the metal target material because they are related to the energy level transitions of the metal's electrons. I don't think you need to memorize what exactly K alpha and K beta are, but you should know that the discrete characteristic X-rays are from energy level transitions of electrons. Now let's take a better look at the continuous Bremsstrahlung X-rays. This curve continues on, so there is no limit on the longest wavelength photon an X-ray tube can emit. However, there is a shortest wavelength limit. This is because energy has to be conserved. When an electron is accelerated by this high voltage, the electron gains kinetic energy. The kinetic energy gain comes from the potential energy loss, and U equals to QV. Since we're talking about electrons, the Q, the charge of an electron, is 1e, so E times V gives us the kinetic energy gain of the electrons. When the electrons hit the metal target, at most, it can lose all its kinetic energy to the X-ray photon. Therefore, at most, the X-ray photon energy HF can be this much. And F is C over lambda. And this gives us the highest energy, highest frequency, and the shortest wavelength X-ray photon an X-ray tube can produce. We will look at a sample problem in the next lesson.